next presentation will be by Professor Emmanouil Kioupakis from the University of Michigan. So as you know, Ron is one of the organizers of the event, and he's going to tell us about Phonon-assisted process.
Thanks, Feliciano. Thanks for the introduction, and thank you all for coming here today to learn about. It's my pleasure to tell you about how to use the APW code to calculate phonon-mediated optical properties in materials. Does that sound okay in the back of the room? Everything's okay? Yep. All right. Wonderful. Thank you. All right. So let's start with this. A little bit of motivation. Like, why do we need to study phonon-mediated optical properties? And I will start with the case of silicon. You may be wondering, why do I need phonons, right? I can use a code that calculates direct optical properties, and like the case you see here in silicon, and I can get pretty good spectra. So what we see here is if we use a code like BethelGW to calculate the direct optical spectra of silicon, including quasi-particle and extonic corrections, we get a pretty good agreement between theory and experiment. And not only that, but also if we factor in the temperature broadening of the states by electron-Phonon interactions, we can also obtain the broadening of the states. So everything looks great, right? So why do we need phonons? The thing is, if you see here, all the spectrum works in the ultraviolet part of the spectrum, right? And remember, this is silicon. Silicon, however, has an indirect bandgap at 1.0 eV, right? So what we see here is we see transitions across the minimum direct bandgap, which is 3.4 eV, and therefore silicon only absorbs ultraviolet light in a direct way. If you really want to understand how silicon absorbs visible light, that's impossible to get with direct absorption. Okay, in order to get absorption in the visible across the indirect bandgap, that's where you absolutely must have phonons. You need energy from the photon for an electron to go across the bandgap from the valence to the conduction band, but you also need the momentum coming from a phonon, because photons carry very little momentum for their energy, in order to enable this indirect transition that changes both the energy and the momentum of the electron. And that's absolutely important, because if you did not have phonons for silicon, you would find that it is transparent in the visible. And as we know, silicon is the most widely deployed solar cell technology that covers roofs and everything. So they wouldn't work without phonons. So absolutely crucial to use phonons to understand not just the fundamental science of optics, but also a very important technological applications for the most widely deployed semiconductor and the most important part of the spectrum. So to discuss the equations that get involved in Phonon-assisted optics, let's start with optics. And we're working here with linear optics, like the equations that describe, for example, how light gets refracted by materials, how it gets absorbed, etc. So when it comes to refraction, we need the refractive index to determine how a material reflects light or how it refracted and changes the angle. In order to describe the absorption, we need to invoke the absorption coefficient alpha that has units of inverse length. And the way it works is that if you shine light in a material, the intensity of the light decays exponentially as the light penetrates the material, with a characteristic length of the inverse of the absorption coefficient. So a very strong absorber, the absorption coefficient is on the order of 10 to the 5 to 10 to the 6 inverse centimeters. So that's 10 to 100 nanometers, and that's where about most materials who absorb strongly absorb all the light. Okay, so our goal here is to calculate the absorption coefficient from first principles and compare to experiments. So that, of course, all these parameters are connected to each other. So in order to describe both refraction and absorption on a consistent footing, we need to invoke the real and the imaginary part of the complex refractive index and the complex dielectric functions. And the two are related. If we know one set of coefficients, we can find the other through these equations. And last, to connect to experiment, we can extract the absorption coefficient from the imaginary refractive index through this equation. Okay, so these are basic equations that describe linear optics in every material, in a metal, a semiconductor, an insulator, a direct or Phonon-assisted. These are the properties we want to extract from our calculation and compare to experimental spectra. So, and that's where phonons come in the quantum theory of absorption, because you can approach absorption in metallic systems, for example, with a semi-classical Drude theory. You can approach the problem as the response of free electrons to a time oscillating electric field. And so you can find things like the connectivity, like the DC conductivity we saw today by Samuel Concept, in his discussion. But also we can find the absorption coefficient if we look at the response to a time oscillating field with a parameter tau. And of course, you can calculate parameter tau. But most of the time, experimentally, people approach this model in a phenomenological fashion. They fit tau to much experimental data without getting insights about what are the phonons that participate, what are the processes that take place. And also, as you see here, this is the, this equation doesn't take into account interband processes, how a single electron can absorb photons and go to a higher state. So that's what we want to, that's why we need to switch to the quantum theory of light absorption that describes all of these processes in a consistent footing. So the way we work here in the linear response regime, so we assume that the light intensity is weak enough so that we can treat it with perturbation theory. This is not, say, a very intense light pulse where we have to account for the dynamics of electrons. These kinds of techniques are more appropriate to handle with perhaps time-dependent density functional theory. But here we're talking about the response of a material to a weak perturbation, where we have to start from the arbitrary state, that is the state of our system as we calculate from a density functional theory or perhaps a GW calculation. And that's what we use to get single particle wave functions and eigenvalues. And our perturbation is the interaction of electrons with the photons. And we describe the photons through the vector potential of the electromagnetic radiation field, which couples to the momentum operator or the velocity operator if we're using pseudopotentials through this fashion. And then we go through Fermi's golden rule to evaluate the probability for recombination, for absorption, or for a transition from state I to state F as a function of time, through a matrix element square times the delta function of energy conservation. So our initial state is the electron in the valence band plus the photon. The final state is the electron in the conduction band for the photon being absorbed. And so we can plug this in and find the also the matrix element between this pair of states. Now, how do we connect to experiment? The absorbed power, the energy being absorbed by our system, is equal to taking into account all possible transitions and all the rates times the photon energy, right? So, so this gives you the entire energy rate absorbed by all the totality of electrons in your system. Now, we have to go back to our electromagnetism and see what is the equation that gives us the incident power, right? That how much power is falling onto the material. And that comes from through the vector potential. So if we do the equations, this is what we found. So if we take the ratio of the two, that's how we find the absorption coefficient. How much energy is being absorbed by our system divided by the energy flux. Okay, and that allows. So in this term, the vector potential will cancel out, so the photon field will disappear, and we're left only with properties of the electrons, like band energies, matrix elements, occupation numbers, and a summation over the Brillouin zone. Okay. Again, this equation is for direct absorption only. There's still no phonons in the picture. Okay. And if you want to find the electric function, the equation for the electric function, you would have to convert the absorption coefficient to the electric function through multiplication by the refractive index and the speed of light. And you find this equation that you may have seen before, where we have to sum over all possible transitions from occupied to empty states. We need the dipole matrix element, in this case from the velocity operator. We need to ensure energy conservation. Electron plus photon give us the excited state. And we have to sum over all the states in the Brillouin zone. So that gives you the imaginary part. Of course, in electromagnetism, we can find the real part through a Kremes-Kronig relation. The two are connected through the causality principle. So by doing the Kremes-Kronig integral, we can find an equivalent expression for the real part. And the small difference is that for the imaginary part, because of energy conservation, if you're looking for frequency omega, you only need to consider states whose energy difference matches that frequency omega. For the real part, because there is no energy conservation, the electric response of a material at frequency omega depends on state at all energies. So that's a big difference between the two. Okay, so epsilon 2 is more easier to calculate if you use a window for states that you're interested in calculating. All right, so far these equations have been done for direct optics. There is no a principle of phonons yet, right? And this you can do very easily with established codes. So how do the phonons come in? Now, if we also take into account the fact that our atoms are vibrating, we have to consider one more perturbation, and that is the Electron-Phonon Hamiltonian. So now we have to go to second-order perturbation theory and use the second-order Fermi's golden rule to find the rate from the intermediate to the final state. And the equation is given by this term where the initial state gets scattered to a virtual intermediate state M, and then to the final state in a second step. So there are two steps in the process, divided by the energy difference in the denominator. And our Hamiltonian is the electron-photon plus the electron-phonon. And so each of these Hamiltonians has two terms. And what we want to do is want to keep only those terms that involve one photon and one phonon. The other two terms describe two photon absorption or two phonon absorption, but that's not what we're looking for here. Here we want the phonon-assisted absorption of light. And so we also end up with two terms because the order of these events may be different. For example, you may first have to have electron-phonon scattering followed by light absorption, or you can first have light absorption followed by electron-phonon coupling. And these two processes contribute quantum mechanically, so you need to make sure we keep track of the phase as well when we take these terms into account. Going back to the diagram, that's how we represent these two terms, right, the two orders. And so once you factor everything in, that's how we find the equation for the absorption coefficient for phonon-assisted optics. Again, it's a double sum over the Brilliant zone for every initial and every final state Q. We also need to account for energy conservation, where now our final state is equal to the initial plus the photon energy plus minus the energy of the phonon that was absorbed or emitted during this process, right? So this conserves energy. The matrix elements now have to be modified to account for the fact that we have not just the electron-photon matrix elements, the velocity operator, but we also have electron-phonon coupling. And we need to divide by those appropriate denominators to account for the energy difference between the virtual intermediate and the final state. And the two possible paths, S1 and S2, correspond to the two different orders. Do we first have the electron-phonon term followed by the electron-photon, or electron-photon first followed by electron-phonon? And so on this sum over intermediate states extends through the entire set of states, both the valence and the conduction band. And at first it may look like, hold on a second, the intermediate state violates energy conservation, right? It also violates Pauli exclusion. We need to sum over this state even if it's fully occupied. But that actually that's not a violation of physics here, because the reason this sum appears is because we are doing perturbation theory. We're just expressing the perturbed state as a linear combination of the unperturbed one, so that there's not like the virtual state is never truly occupied. So that's why we can do the summation without violating these fundamental laws of physics. Okay, so the sum extends over all states, both occupied and not in this energy. And the last factor is the occupation numbers, because we have to go from occupied to empty state. So we need to account for the occupation numbers of the initial and the final state. And also we need to absorb or emit a phonon. And so the phonon occupancies also enter the equation. Again, the electron-phonon coupling can be either absorption of a phonon or the emission of a phonon. And phonon emission actually is important here because you can always emit a phonon, right? You don't need to have a phonon there in order to emit it. And usually when we talk about semiconductors, the band gaps involved are of the order of electron volts. So the photon always gives us enough energy in order to emit the phonon and make this process possible. And so what I find surprisingly is that phonon-mediated processes are possible even at absolute zero temperature. And in fact, they're actually quite temperature insensitive, because you can always emit a phonon, and the phonon emission term is not so dependent on temperature. So that's kind of counterintuitive for a phonon-mediated effect. Okay, so these are the main equations, and our task now is to implement this in the APW code. Now, I want to emphasize a little bit why this is relatively recent. Why has this been done from the early days of DFT? And the reason is the double sum. When you look at direct absorption, as remember, the photon gives you energy but not much momentum. So in this energy momentum diagram, the optical transitions are vertical, right? They transfer very little momentum. So when you do a sum for all processes, you only need to look at direct transitions, you have a single sum over the Brilliant zone. For phonons, though, you have to account for every possible wave vector in the valence band, and your final state can again be another vector across the entire Brilliant zone again. So you have a double sum here. So you can calculate electron for a single phonon. You can calculate all these terms even on the laptop in a matter of seconds, right? It's very quick. But if you want to have a fun enough energy resolution, so we look at the bands here, we see the bandwidth is about a few EVs. If we need a resolution of a few tens of millieVs, that means we need to take points on the order of 20 by 20 by 20 or so, right? And so we end up with hundreds of millions of combinations, right, of initial and final states. So even though each of these calculations is quite doable, the totality of the combinations is impossible even on the most powerful supercomputers if you want to go by brute force. And that is why we need to use Wannier interpolation. That's why this has not been done without a code like APW, which allows for the efficient interpolation of the matrix elements. Because by switching to the Wannier basis, now we have a very efficient way to interpolate the quasi-particle energies in the band structure, the optical matrix elements, and we can do this with the Wannier 90 code. But most crucially, we need the Electron-Phonon Kavli matrix elements. That's what we're obtaining from EPW. And if you factor all this together, then we can get a Phonon-assisted spectra. Now, let me make a brief comment about how do experimentalists measure band gaps, right? So they do optics, and they try to look at what is the onset of absorption, right? And so below the onset, absorption is weak. Above the onset, gets strong absorption. And in fact, there are measurements that they do in order to determine whether a band gap is direct or whether it's Phonon-assisted. And the way they do this is with the so-called Tauk plot. So what's the idea behind the Tauk plot? The idea is that if you have direct absorption, your absorption coefficient has an onset at the direct band gap. So if your photon energy is above the direct band gap, you have absorption. And the offset has a square root-like behavior. In contrast, when you have phonons, the dependence goes like the square. It has to do with the different density of states that appears in the equations. So what do experimentalists do? They take their measured signal, multiply by the photon energy, and then square it. Okay? And then that equation should give you a straight line with respect to the photon energy, like you see here. So this intercept gives you the direct band gap. Now, if you do the same process, but instead of squaring, you take the square root, you'll find a straight line, and that will give you the indirect band gap. So if you have an indirect gap material, one process will give you the minimum indirect band gap, the other will give you the minimum direct band gap. Okay, and so the exponent makes the crucial difference to tell us which kind of band gap we have in our material, right? So for Phonon-assisted processes, we need to look at the indirect absorption, and so we need to, when comparing to experiment, we need to keep this into account that this is what experimentalists measure and we can compare to. And that's what you see here. So here you see the calculated data for the absorption onset of silicon in comparison to experiment. And that was calculated with EPW back in the early days in 2012. So what you see here is, again, the absorption coefficient times the photon energy raised to the 1/2 power in order to look at the indirect absorption. And that's what you see here. So we see very good agreement for the shape of the spectra. Again, we see the linear behavior coming from the onset of indirect absorption, and a slight dependence on temperature because of the phonon corrections to the band gap. Now, I want to mention here that in order to make this comparison, we had to shift the energy of the theory spectra by a rigid amount that varied on the order of 0.1 eV in order to match experiment. And then there are two reasons for doing that. One is we did not take into account the effects of phonons and temperature on the eigenvalues themselves. And the other is the inherent accuracy of methods such as DFT and GW in determining band gaps. So there's always error bars on the order of tens of millieVs, which we need to improve on the methods in order to ensure accuracy of experiment. But if you take this into account, just the shift of the onset, you see that the spectra come in very good agreement with experiment, and here you can see the contribution by phonon absorption, the contribution by phonon emission, and so the different onsets corresponds to plus or minus the phonon energy, as well as the temperature dependence. And so that's good. Now the spectra here, though, we can still model somehow if you take an effective Electron-Phonon Kavli matrix element, an effective dipole matrix element. But the true power of the method is when we go deeper into the visible, where states throughout the Brillouin zone participate in the absorption. And again, here we see an excellent agreement with experiment. The coefficient much as well over several orders of magnitude. Again, we have shifted the onset here to match experiment, but without this, just with this one parameter that changes the onset, you see that we do the spectra pretty well. And so the theories from 2012, experimental data from the 1950s. So we'll see that now we have the capability to go out there and predict the optical spectra of semiconductors entirely from theory. And I want to emphasize on the entirely from theory part, because that's what we have also done for a new semiconductor like boron arsenide. Now, boron arsenide is a very interesting story. I don't have time to cover it entirely, but it's a new material. It crystallizes in the zinc structure, just like gallium arsenide, except you have boron and arsenic in a cubic crystal. It was theoretically predicted to have an unusually high thermal conductivity. And the reason has to do with the mass mismatch of the very light boron atom and the very heavy arsenic atom. It's a very beautiful prediction that was amazingly verified experimentally as well. Experimentalists were able to synthesize bulk zinc crystals that verified the predictions, and a beautiful example where theory guides the experiment. Now, when we found out about this new material, we were of course very excited to go and calculate its properties such as the band structure, the optical spectra, and everything. And so Kyle, who's right here in the room, Kyle, raise your hands, right here, we'll keep later with exercises, did the calculation and a standard GW calculation to find the band structure, and he predicted a band gap of 2 eV, 2.05 eV, and a direct band gap of 4 eV. Okay, and at the time there was no experiment. Actually, there was experiment, and they said the band gap was 1.5 eV. Okay, so we're this place where we are in a major disagreement with experiment. But this is where we need to trust our methods, that we know we did things right, we know that our methods do work, and we published it. And Kyle's a very brave man, and we published this result. And because we knew it should come out correctly. And long story short, the problem with the experiment at that point was that the samples were not of good quality. Those early experiments were done on quite defective samples, perhaps powders. It wasn't the high quality of samples that were synthesized in 2018. But when they did optical measurements, this is a collaboration with a group of Professor Gangchen at MIT, we saw that indeed, experimentally, the band gap was indeed around 2 eV, verifying the theory predictions. And we also were able to calculate the Phonon-assisted spectra for the indirect band gap. And again, you see the magnitude of the coefficient is in very good agreement with the experiment. The experiment has been shifted upwards to change the different offset, but you see the slopes here are the same. Both the indirect band gap as well as the direct band gap. So again, another case where theory was able to take the first step and tell experiment what the value would be. So, and subsequently predicted experiment, verified experimentally. All right, now I'm going to switch topics a little bit and go back and discuss the case where we do have metallic carriers, meaning free carriers that can also absorb the light. Going back to the case of absorption in metals. Now, why I mention this? Suppose you have silicon, and suppose you use a photon energy that is below the band gap, right? So the band gap of silicon, 1.1 eV, we're talking about photons with energies of 1 eV or less, right? In an ideal situation, those photons should not be absorbed in silicon. It should be transparent. However, most semiconductors like silicon are usually doped. They have defects. And those defects can absorb even photons below the band gap. No material is truly transparent. Even water is not transparent, right? If you go deep enough in the ocean, it is dark, right? So we need a theory to account for how sub-band gap photons can be absorbed by imperfection of the material, and in particular by free carriers semiconductors. So the idea here is that the photon can be absorbed by a free electron at the bottom of the conduction band and go and occupy a high energy state. That can happen directly, just like we know about semiconductors. It can be happen through the assistance of phonons, just like it happens across the indirect band gap. Now we have an intra-band process, or it can happen through a resistive process, like those electrons also respond to the field in a collective fashion, like an oscillating electromagnetic field, and we have a plasma. And because material is resistive, we're going to have some loss. Those oscillations of the charge are not for free. After a while, they dissipate. Your energy gets lost through phonons. So we can calculate all of them. And here's what we see. So what we see here is we're looking at sub-band gap photons, right? So here's our band gap. This is the decreasing photon energy. Right, so here's where you see the band gap coming in and you have strong absorption. But if you focus for energies below the band gap, you see we have contribution by all these terms. We have a direct transition for electrons from the lowest conduction one to the next one. We have Phonon-assisted transitions, again, these kind of interband processes. And we also have resistive losses. Charge impurities end up not being a very important factor in this case. But if you sum them all together, we get a curve that looks like that. It's an increasing curve with increasing wavelength. It has this little bump here, this little shoulder, which seems unusual, right, for a spectrum. But interesting thing is, that's what we see in experiment as well. There's this extra bump here coming from the direct transition between the two large conduction bands in silicon. We can apply the same thing for holes as well, except the transitions happen within the valence band. And what we see is, again, we have a direct contribution from the first band to the second one, like this. We also have phonons, we have charge impurities and resistive contributions. The term is more monotonic here, but as you see, all the terms have similar magnitude. So we have to account for all of them on a similar footing. And if we, oops, sorry for that, if we sum them up, we see that again, we find a very good agreement with experiment over a range of wavelengths and doping concentrations. So now you see that we can account not just for transition across the band gap, but also for how doped materials can absorb subband glide. In the case of silicon, how it can have an impact on, say, silicon photonics, how silicon can be used in telecom wavelengths for photonic circuits, etc. So if you understand more about this work, of course, Xiao is here. Xiao can raise your hand as well. Yes, Xiao will be helping you with the exercises for Phonon-assisted optics. And you can also read about this in the paper I will just post on the archive earlier this year. All right. So in the remaining, I will discuss a few more applications of the absorption of light by doped materials. A very common case is when we have transparent conducting oxides. Now, in many applications involving light, we need materials that can conduct electricity while being transparent. So metals are great conductors, but they are opaque. So we can't use just metals, they would act like a shadow. Insulators are transparent, but they don't tend to conduct. So the best balance happens when we have materials with a band gap that exceeds the visible range, but are dopable. An example is tin oxide, for example. Tin oxide has a band gap of 3.5 electron volts, but you can dope it. You can replace oxygen with fluorine, gives you one more electron in the conduction band, and it conducts. I apologize for the scrolling. Now, again, if you look at transitions from electrons in doped tin oxide, vertical transitions are impossible in the visible because there are no states for those electrons to go to. The states you need have a different K, right? This is the energy versus K relationship. So you need both energy from the photon and momentum from a phonon or impurity in order to reach those states. So another case where Phonon-assisted optics is important to find how those materials, which we want to use as transparent contacts, are actually losing their transparency. So do the calculation. Again, we're looking for the absorption coefficient. And just like the conductivity is proportional to the doping of your material, so is the absorption. The absorption is proportional to the doping. The more carriers there are, the more they absorb. And the proportionality is the absorption cross-section. So that's what we calculated for tin oxide. Again, this is for sub-band gap photons, which here includes the visible. And we find, so what is the fundamental limitation to how transparent these materials can be? So you make them more conducting by increasing the doping. That comes at the price of reducing their transparency. So that's a fundamental limit of the absorption. And we've applied this technique to understand the free carrier absorption loss in materials such as tin oxide and indium oxide, and famous ITO that is used as a transparent contact. And I want to conclude with one more application of where free carrier absorption is important, and that has to do with lasers. So today we have very efficient semiconductor lasers in the violet, in the red. They're very portable. We've all used the red laser pointer, right? And we can use them for optical storage. And the big goal is to use them for laser projectors. Now, there's a challenge for green lasers, because if you ever use a green laser pointer, you notice how much bigger and heavier they are compared to, say, the red ones. The reason is green laser pointers use a bulk crystal in order to do frequency doubling of an infrared laser. So they're very inefficient, they're bulky, they're slow. So the goal is, can we use direct emission from a nitride material to make a laser? So in order to do that, we have to again consider how a laser works. And here's a cartoon picture of how a laser works. So to make a laser or an LED, with semiconductors, you need a so-called PIN region. You need the p-type material that conducts holes. You need an n-type material that conducts electrons, and those are typically, gallium nitride. And you need in the middle an undoped region where the light emission will take place. So you apply a voltage source, and the voltage source takes electrons from the p-type region, moves them around the circuit, gives them energy, and puts them in the conduction band of your n-type region. Now, those electrons and holes find their lowest energy state. The electron falls in the quantum well because that's a lower energy state. The hole rises like a bubble to the highest valence band. And so you confine the electron and the hole in this active region where they recombine and emit light. That's what you want to do. So in an LED, you want to make the structure thin and compact and get those photons out as fast as possible without having to cross too much material and get absorbed. In a laser, however, we don't want the photons to leave the material right away. In a laser, we want to have stimulated emission. So we want the light to bounce back and forth for photons to multiply to cause stimulated recombination and get a coherent light source. So the way it works is that if you have a passive medium, we have absorption, meaning that if you have more electrons in the ground state than the excited one, then as light propagates, it gets absorbed by exciting electrons across from the low energy to the high energy state. And that gives the absorption coefficient. Something more interesting happens, though, if you go through an active medium, a medium where you have more electrons in the excited state than the ground one. Then when the first photon comes, it induces the electron to recombine with the hole and creates a clone of the original photon. They have the same direction, the same energy, the same momentum, the same phase, right? And so as the photons bounce back and forth, they cause more and more of these recombinations. The energy, of course, is coming from the circuit. And that's how you get gain. You get a material with a negative absorption coefficient in a specific energy window. And that's how you get lasing in a semiconductor, in a gas laser, in a solid state laser, in any, you need a material with this negative occupation. So the difference between gain and absorption is what gives you the net output of the laser. And of course, if absorption wins, you don't get lasing, right? So that's the case in the night eyes, because now we have to use photons with energy below the band gap and see whether they can be absorbed or whether they will be amplified. So again, the surrounding layers here are doped. So that's something to consider. So we don't have absorption across the band gap of these materials, but because they are doped, those free electrons at the bottom of the conduction band can absorb the emitted light, or those holes can absorb the emitted light. Again, this is a process where we must involve phonons. The direct absorption is just too weak to explain what is going on in these materials. And so we do need phonons, because once you have phonons, you get absorption for any wavelength of light, both by electrons and by holes. So we did this calculation, and we found the spectra. And again, we found that, of course, the result is not zero. We do get a loss. And the most important loss comes actually from the holes. They have a high density of states. They have strong electron-phonon coupling, so they're much more important in causing energy loss in these materials. So if you could summarize this technical aspect, so what we find in the end is that indeed it is the p-type region of those lasers that causes the loss and limits the output power. In particular, what is difficult in gallium nitride is that those acceptors have a very high activation energy. So although we put a high concentration of magnesium, only a fraction of it gives you free holes. And you end up with a very, very high concentration of magnesium acceptors which are not ionized. So those holes which are here still trapped to the magnesium donor atoms, you see in this cartoon picture, those holes do not conduct electricity, but they can still absorb light. So even though they're not active from an electrical point of view, they are still active from an optical point of view, and they cause the optical loss. And that was able to explain why the absorption in the p-type layers of a laser device is the crucial loss. So that proposes a design strategy where we can engineer the photonics of a laser in order to avoid having the photons, the optical mode, reaching into the p-type regions, and so reduce the absorption and improve the output power. So another case where, again, predictive calculations can explain what goes on in lasers and how to design better devices. All right, so some other applications of Phonon-assisted optics, again, they're very important in the case where you have free carriers. And an example here from the work of Brown and al. From 2016 is the case of metals, right? So metals do have free carriers, you can also have a Phonon-assisted transitions. You have direct interband, direct intraband, and also the internal resistive losses. And all of those are the cause of the optical response of metals, including the effect of plasmon decay, right? So a plasmon is a collective excitation of all those electrons in the material. That is not, that excitation does not live forever. A plasmon decays because electrons and holes scatter and lose energy to the phonons. So that's a major limitation in plasmonics. The fact that once you transfer the energy from the photon to the plasmon, the energy can be dissipated, right? So you lose the coherency. So this study explains the limitations of plasmonic materials in terms of how long they can retain the plasmon oscillation. And so we see again here, we have a strong contribution from the Phonon-assisted term. So another application of Phonon-assisted optics. And before I conclude, I want to also emphasize one method developed by Mario Zacharias, who's also here with us today, and he will give us a presentation on Friday on this method. It is the method of directly calculating the Phonon-assisted spectra in a single optimal supercells. So we take the material, we make a supercell, and we displace the atoms, but not in a random or a thermal statistical fashion, but a very specific linear combination of the phonon modes. And by doing that, we're able to get the Phonon-assisted spectra as well in excellent agreement with experiment. So by working with a supercell, we get several advantages, such as we can avoid the divergence, we don't have to do one interpolation, and to get those properties. We can also naturally include the temperature dependence of the eigenvalues and the band gap, as well as get a Urbach tail for the absorption, and can be generalized to other functionals. And also, there's also work where this method is being combined with excitonic effects, and you can also combine it with the effect of excisions. So for more of that, this is one of many papers from Mario where he discusses this method, but also you can hear more in his talk on Friday. So again, if you're looking for a broader spectrum, you can do supercells. That's another method you can consider as well in the calculation of the optical spectrum. All right, and here's some references that I'd like to share with you regarding both direct as well as Phonon-assisted optics, both reviews of the field as well as papers that discuss the specifics of the implementations I discussed with you today, and also look forward to the new technical EPW paper that will appear shortly. And well, I'd like to thank the developers, both my group as well as the collaborators that we have worked over the years who work on this project. And of course, thank you for your attention. Thank you very much.
Further interesting thought. So I'm curious whether in this way, Urbach tail can be captured.
Excuse me?
Urbach tail.
Oh, the Urbach tail, yes. I do not think it will be captured. We do not have the Urbach tail. So the tail you may see here comes from the fine broadening we do to sample the Brilliant zone. So in order to capture the Urbach tail, you will need to see what is the effect of phonons on the eigenvalues, a statistical description of the energies. And so that will give the exponential, you get a statistical distribution of the localization of electrons and holes, and that will give you the Urbach tail. So this method, we don't have to take the eigenvalues, we just get the spectra given, we fix the eigenvalues, but with the method that Marius will discuss, you can get the statistical description of the variation of the states, and that's why you can capture Urbach tail as well. Thank you. And also, I want to mention also the Urbach tail also can be affected by defects as well. So the two are the phonons is one part, but also more defective samples have longer Urbach tails. So that's another source that of the Urbach tail in experiments too. Thanks.
Great. Questions?
Yeah. So repeating the question for Zoom. So the question is whether this technique can capture excitonic effects. You're right that the theory can be generalized to excitonic states. So now we're looking at single particle excitations in the way it's implemented in EPW. The method developed by Marius actually can do excitons. if you can afford it to do them for the supercells needed. So yes, it's a great question. It should be important to consider. We haven't done it yet. I know that there is a work from Boston University that has looked into the effects of phonons on the exons in 2D materials. And also, I think also the developers were involved in that work. So I can share with you later, perhaps. I'm sorry not have this here today, but I'd be happy to point this out to you. Mm-hmm.
Thank you for your talk. With the thermal dependence, have you found that you're able to accurately model items like thermal LO scattering in on cascade lasers?
So your question is if we can study some such a recombination, phonon-mediated recombination in quantum cascade lasers. It's a good point. We haven't looked into that. I would suspect it's probably a direct process, more likely than the Phonon-assisted one. But yeah, you can calculate if you have the optical matrix element. I apologize. I have to go back to many slides. I apologize. But perhaps maybe this report can tell you more about the Phonon-assisted optics. Sorry, the direct optics. Then you can calculate that. For lasers, if you're going to change the scale of your simulation, maybe atomistic is not the best way to go. Maybe you can use device simulation software that can capture heterostructures that can be informed by first principles parameters. So like the effective masses, matrix elements, and everything. And using that, this combination of software, you can perhaps study more accurately a whole device that involves both excitons and electronic transitions. I'll be happy to point you to this direction afterwards, but I think, yeah, we may need a few steps, but I think it's totally doable. Thank you.
Other questions?
Mm-hmm.
Yeah, thank you for the lecture.
Thank you.
I was just wondering, in direct absorption, does the intermediate direction energy have to be a band?
If the intermediate has to be a band, your question is if in the equation for Phonon-assisted optics, if that intermediate, I apologize for making everybody dizzy. Back to in these equations, you mean, right? In this intermediate state, yeah, it has to be one of the bands, right? What we're doing here, we're expanding in some sense the perturbed wave function is a sum of the unperturbed ones, right? A linear combination of the unperturbed ones with these energy denominators. So we use the unperturbed basis as a basis to expand the perturbed wave function, and that's why you find these states here. Thank you.
Okay. Any questions? This one?
So there's one on Zoom. Okay.
They overlap with the Electron question, but the question is in E16, the exotonic effect is not included. How can the computational result be in such good agreement without with the experiment when you neglect exotons?
Yeah, that's a good question. I think so, particularly for silicon, exotonic effects may affect the spectra, but they don't change the peak position just because exotonic effects are weak in a bulk semiconductor like silicon. So. And we see that also in the direct spectra where excitons change the peak amplitudes, but not the peak position. So, and that is usually by a factor of 2 at most for material like silicon. So I also suspect that in the case of an indirect gap material, that the exotonic effects would be in general weaker than a direct gap material just because of the separation of the electron and the hole in momentum space now. So those coulometric elements won't be as strong as a direct absorption, but of course, if we're doing the calculation, I won't be able to tell for sure, but that's a great topic to explore. I agree.
Okay, so if there are no other questions, so we can close the session here. Let's thank Emmanouil and all the. So now it's time for lunch, and we resume in I think an hour.
Very much. Oh, no, sorry. Sorry. Oh, good. I'm forgetting this one.
So about so I understand how indirect captured by phone. I'm curious about